myself. My name is Mauro Filippini. I'm an assistant professor at the Politecnico of Milan, just 100 kilometers roundabout east from here. And I will present the result of a test campaign made on case carburized gears, made in cooperation with Augusta Westland and of course our department. So basically my talk will be more focused on industrial or practical aspect of the fatigue, and this presentation is somewhat derived from a previous presentation made recently at the AGMA Fall Technical Meeting, the American Gear Manufacturer Association technical meeting, and the topic is the single tooth fatigue test on aerospace gears. And I will speak about the test scheme and the test rig design, which is relevant for deriving the fatigue data. I will speak about the test groups and with a special focus on the material, how these gears have been designed and how are produced. And we have been making some comparative tests up to 10 millicycles and an extended test up to 100 millicycles for just one test group, and also some we have been doing also some ultimate load tests, because these are relevant data that can be included in the design of gears for aerospace transmission. One of the problems in helicopter design is that the industry wants to redesign or to ensure that they can increase the payload of the helicopter, of the machine. So they want to know exactly how much they can increase this payload, or if they can increase the durability of the component, the duration of the component without maintenance. So one of the aspects, the transmission is the real heart of the helicopter, and the basic part of the helicopter is the transmission. And actually, in the design standards, which are commonly employed for designing the transmissions, you will see that after 10 to 10 power 6, 10 to the power 7, there is a gray shaded area, which is some way it's a lion land. So nobody knows what's happening in this region. And there is this is the graph, the shape curve that is contained in the AGMA standards, and on the left, on the right side, you will see the ISO standard corresponding curve. And in the AGMA, you will, if you can read, they say that these curves depends on the material, on the geometry, on the manufacturing process, without specifying which real curve to use. So basically, the interest of the industry is to know whether you can take a definitive fatigue limit, or you have an endurance, and how is it, how you can, which is the slope of these curves in this region. So there is a real industrial interest in this region on the SN curves. So there is a limitation of rating standards due to the shape of this curve. So how are bending fatigue tests performed on gears? Usually for bending fatigue test, you need a special rig in order to load one tooth at a time. So basically, there are two special conception of this test rig. The one is the upper one is is more used in the US, and then where you load one tooth on the single highest point of contact, and the other, and this tooth is just loaded at the base, so it just you just need to block the wheel, and the wheel, the gear wheel is pinned, so the position of the load is determined just by the position of the pin. In Europe, especially in Germany, they use more frequently this configuration where you have two teeth that are loaded at a time, and the gear blank is not supported. And the principle is to use the Wheel-Double-Span principle to load the two teeth. So we design a special wheel for this research program. So the wheels are being designed in order to have 32 teeth, and the modulus and the shape of the wheel has been designed in order to have the possibility to reproduce the common procedure used to produce the wheels for the real component, but this is not a real component. I mean, it's a special wheel designed for deriving fatigue test data. So we employ this test rig in which we have this pin that can be removed after positioning the wheel. So the modulus is very little, and in this way we ensure that we have a proper positioning of the wheel at the beginning of the fatigue test. And here you will see, you don't hear the noise, but this is the result of the final seconds of the fatigue test. So basically all the life in our test have been spent in initiating a break, and just these few seconds are the last one where you see that the wheel is removed from the two ampoules. Okay. So these are the gear data, and here you will see that we have tested 4 different materials. Well, 2 different materials and 3 different conditions. So we have this 9310 steel, which has been vacuum induction melted and vacuum up remelted, and the manufacture of the wheels is with ground fillet and shot pin after case hardening. And here we have an unground fillet where you have the root fillet which has been cutted by generation. And then we have 2 different materials here. This is only vacuum arc remelted without the vacuum induction melting, and this is a different material. Okay. So basically, the way that to design the gears is to have a transfer between the load Ft and a stress, and there are different methods to correlate the force, the applied force, to the stress. And so here you see that for the ground and unground fillet there are different correlations between the load and the stress you can get from FEM calculation or by applying spring gauges on 2 teeth in the same configuration that has been employed in the test. Of course, the AGMA rating standards give different figures. But actually, AgustaWestland has a previous experience of using some shape of the curve. So we derived the fatigue data and we used the same procedure that are currently used by AgustaWestland to derive the fatigue curves. And basically they use this 4 parameters shape curve. And we have made the best fitting of data on this formula. These are the best results for the 90% steel with the ground fillet and shot pin. And here you see that we have tests up to 100 million cycles, and in this range we have had 2 failures. In the data fitting, all the points have been considered as failures because we have the tests have been the fitting of the curve has been used by standard least square method, and so here you see that we have 1 point here which represents the ultimate load. So we forced the curve to pass through that point, and then we made the data fitting on the other test. Of course, you cannot rely on this part of the curve because it's meaningless, but this part is currently represented by the formula which is currently employed in the practice of designing Pearson transmission in this industry. And here you see that in this case, for the unground fillet, we had either failures below 10 power 6 or run out. We have a mixed behavior, so probably we will need to make some other tests in this region to confirm this data. And then this is without vacuum. So just the vacuum arc melted material, and this finally the PyroWare or AX53 material. So just a final comment. This is a special curve which is currently employed by the industry, but we don't suggest them to use this data. But you can compare the so-called fatigue limit. Well, it's an endurance limit at 10 power 7 between the different conditions. So in the first phase, we consider just the test up to 10 power 7, and in the second phase, we consider also test up to 10 power 8. And we have a small difference, which has to be attributed to the way we perform the data fitting, not a real or a consistent reduction of the fatigue limit between the 2 test set. And here you will see also the fatigue limit in terms of stress for the other conditions. So it's rather high for conventional materials, but this is due to the presence of high residual stresses and the high gradient that we have in the tool. So, as I told you, we performed also ultimate load test because there is a need in the rating standard to consider the ratio between the ultimate load to the fatigue limit ratio. This is a parameter for the rating standards, and we found those figures which are consistent with the current practice and the ISO standards and the AGMA standards for So a second observation was there was an extensive observation of the failures. Just in one case over all the tests we performed, we got a failure starting from a metallurgical defect. This is a concentration of chromium, which is typical also in bearing steels. You can find those features also in bearing steel. In all the other cases, we found either fractures starting from the surface, or it was really impossible to determine which was the failure initiation site. So we knew that the failure started from the surface, but we could not detect on the entire width of the gear which was the position of the starting position of the failure. And here, of course, you can see crack roll marks, but this is already in a region where you have high plasticity and you have a fast propagation. This is not a region which is in the case hardened layer. So, and we could not observe also, we were not able to observe any failures starting at the interface from between the case hardened layer and the hardened core. So no failures due to the crashing of the interface between the hardened layer and the inside of the material. So I come to the conclusion. This activity is going on. We have been, we need still to analyze the data more in detail, but we have the possibility to say that we have a precise information on the fatigue endurance. Fatigue limits will be too strong, probably. On the fatigue endurance of the 4 test group, both in absolute and relative terms, we have made the analysis of the result with different models of the fatigue life. Of course, this activity must be refined, because at the moment we are currently analyzing the data with the common practice of the industry. We can sum up the 2 phases of the test. We have tested up to 100 gear-proof specimen with a duration up to 10 millicycles for each test, with 430 millicycles totally. And we have a phase 2 test on just one variant with 8 specimens up to 100 millicycles with 734 millicycles. And this very high cycle, we call it very high cycle fatigue test, confirm the estimation done on the basis of shorter tests. So this is give confidence to the industry to their common to their actual design procedures. Now this way to use the real fatigue data has been integrated in the design process of the industry, and if they will change the material, they are planning to repeat the necessary tests in order to confirm that they are doing it the right way. And actually the test program is going on with nitrile gears, because this is the other variant they are employing. We are starting, and in a few weeks we will start test with the low cycle range, just to fill up the land of nobody that is in between 10 cycle, or let us say 1,000 cycles up to 10 power 6. And we will also make tests on the variable amplitude loading, because this is of course a service condition that is of interest in this industry. And we will also do back-to-back rig tests, because you need to transfer the result made on single fatigue test onto real component where where you can have failures, where you have a statistical effect to detect that you are testing all the teeth in 1 year. So I thank you for your attention and just move you